Welcome everyone to the 2022 SciPy Tools Plenary. First, I'd like to start by introducing my co-chairs for this. I'm Thomas Caswell. This is also co-chaired by Madika Monk, Kira Evans, and Monica Bobra. So this is a bit of context of what this is. The SciPy Tools track is an opportunity for projects to provide quick updates to the community. We aim to have a mix of established, well-established projects and new projects that are just starting, as well as general projects and domain-specific projects. We're lucky enough in this community to have a tremendous number of projects we could bring up here. So it's difficult to choose, and we apologize to anyone who wishes who we did not invite. To get us started, I'm going to hand off to Zach, who's going to tell us about Hypothesis. And up next is Tyler with SciPy.
Thank you, and good morning, everyone. I've got 5 minutes to talk to you about a tool update around Hypothesis. And to do that, I wanted to give you a bit of background about property-based testing, which is the general field that Hypothesis is in, and how we can use that to write better tests for the whole scientific ecosystem, whether that's library code like NumPy or end users in science and data science applications. The basic idea is to write tests that Karl Popper would approve of. Tests that don't just demonstrate some particular claim that if you call your function on this input, you get that output, but that could actually falsify a general claim about the way your software works. And so my basic case is that hand-picked examples shouldn't convince us of anything as scientists. But if we have a framework that can generate many hundreds or even millions of arbitrary examples, and none of those falsified the claim, then we're probably onto something. So what might this look like? In a traditional unit test, you specify what the input and the output should be. Taking sorting as the example, if we sort the list 1, 2, 3, we expect 1, 2, 3. If we sort 3, 2, 1, we expect 1, 2, 3. If we sort B, C, A, we expect A, B, C. Make sense? I'm seeing blank faces. Okay, nods, great. If we don't want to write down the output by hand, and anybody who's tested with arrays or data frames knows that writing your output by hand can be a real pain sometimes, we might want to use some kind of trusted implementation. And this does come up sometimes. We might re-implement a more specialized function for higher performance, or we might be comparing a single-threaded and a multi-threaded implementation. But sometimes in science, we have to do things where we don't know the answer in advance. That's kind of what science is sometimes. But even when we don't know what the answer should be, we can often check that we didn't get a wrong answer. In the case of sorting, we can check that the output is in pairwise order and that we have the same number of unique elements. In a physical simulation, we might check, for example, that energy is conserved. With other libraries, we might check that if we save data and then we load it, we get the same data back. So these are quite general tests, but they're remarkably good at finding edge cases. This test, for example, we can feed arbitrary lists generated using Hypothesis. So this is any list of either a mix of integers and floats or any list of strings. And if you run this test, it will actually fail because we forgot about not a number. Who here has ever had a bug due to not a nan? A lot of us? Yeah, okay. So to sort of summarize the property-based testing part, testing science code is genuinely difficult because being science, we often don't know what the correct result should be. But we often have very powerful invariants and properties where we have conservation laws or round trips or physically plausible bounds or self-consistency checks that we can do. And science is also a domain where I would argue we need better tests because we do have bugs in this critical software. So Hypothesis is the library that I lead. It's almost a decade old and fairly mature, I would say almost complete. And we'll be running a sprint to add polish, integrations, and more performance. Lots of people already use it, including many projects that you might have already seen. And I want more people to write more tests. Thank you very much.
Thank you. So up next, we have Tyler Reedy to tell us about SciPy, and on deck, we have Matt Craig with Astropy.
So SciPy provides scientific computing algorithms. It's near the base of the scientific Python computing ecosystem. It's pretty widely used. The picture here is for the Mars helicopter. It's a pretty sort of popular example of the usage of SciPy. We also provide algorithms for things like computational geometry algorithms, the KD tree shown in the middle there, and statistical distributions, a whole bunch of different scientific computing algorithms. One of the big updates I want to tell you about today is our build system overhaul. So the team has actually managed to cut the build time down by almost an order of magnitude on some platforms. So on ARM, this node here took half an hour to build SciPy from source, and now it's taking about 3.5 minutes. So that's a pretty huge improvement for those of us that are working on SciPy or evaluating code contributions. If we wanted to get even faster than that, we'd probably have to break the code into smaller compilation units. So take like the C++ code and divide it into smaller pieces. But we don't have plans to do that at the moment. We've also got a new developer CLI. This uses technologies in the open source community like Rich and RichClick. We're hoping that other open source projects in the ecosystem will eventually adopt this developer CLI as well, so that you get a sort of common experience. If you switch from one project to another, you have a similar development experience, so we're hoping other people adopt that as well. And over the past year, we've had one release, and there's another one that's hopefully coming out in a few weeks. There's a new sparse array API that we've added in for testing. That's a pretty big addition. The sparse SVD library ProPack is now available if you opt in. We've started to, well, actually, we've completed privatizing namespaces that were public but weren't intended to be, so that frees us up to do some development without exposing unintentional public APIs. And for the new release that's coming out in a few weeks, there's some new mixed integer linear programming functionality, some new stats functionality for fitting discrete and continuous distributions to data, a new global optimizer, and our documentation has also improved substantially. And finally, I just wanted to mention some things about sustainability. So we've just recently got some good news with the NASA ROSAS grant, which is a little over $1 million. Quantsite is leading that, and then LANL and Cal Poly are subawards on that grant. There's 4 NUM-focused small development grants. The CZI EOSS Cycle 4 grant, so Melissa, she is leading that effort with, in collaboration with Pandas, NumPy, Matplotlib, with onboarding, contributor experience, community organization, and DEI. I should emphasize that a lot of these grants are collaborations between the different projects. Tidelift and Quantsite, that funding drove some of the build system improvements. We have 3 new team members, Atsushi, Albert, and Tirth, and come join us for the sprint this weekend.
Thank you very much. So up next, we have Matt Craig to tell us about Astropy, and on deck, we have Jim Proversky to tell us about Awkward Array.
Good morning. My name is Matt Craig. I've been a core developer on Astropy for several years. I've got 90 seconds, so I'm going to skip the rest of the introduction of myself. A couple of highlights. We did a new long-term release, or long-term support release, this past year, and another paper about the project. We've also received NASA ROSAS funding and adopted a formal governance structure in the project for the first time. So about 10 months ago, the first election for our coordinating committee was held. I was fortunate to be one of those who was elected. And I'm going to seize the opportunity here of the recent JWST images to recognize on behalf of the coordinating committee and the project the efforts of the software engineers at Astropy and on these projects who made this all possible. So please take a moment to join me if you're an astronomer, or if you liked the web pictures you saw yesterday, JWST pictures from yesterday. Give them a round of applause. As you can see from the graph in the upper right, our contributor base is fairly strong. We have 20 committers a month on average, roughly. What's hidden there is that many of the critical operations like merging pull requests, doing the releases, that sort of thing, rest on the shoulders of just a couple of people at any given time, often under-recognized for that work. And I think that's where I'll wrap up because I see Thomas coming.
Thank you very much. So next up is Jim to tell us about Awkward Array, and on deck we have Jared Millman with Spec.
Okay, thank you. So Awkward Array, in case you haven't heard of it, is a library for doing NumPy-like manipulations on complex data structures, so JSON-like data with full complexity. Even just like if you have a lot of ragged arrays, it's useful for that. So where we are in this, this has been in production for a while. It started in the particle physics community, and it's heavily used by particle physicists, but it's more general than that. The 1.0 branch is in heavy use. It's in production, but we are putting in some infrastructure changes in 2.0, so we're rolling that out slowly for testing. So actually, both versions are available. They're both released right now. One is a submodule in the other. And the major updates for 2.0 involve things like we're replacing our in-house lazy arrays with Dask, a new Dask collection developed by Doug Davis. More interoperability with more array libraries. CuPy, JAX, AutoDiff was added recently. C++ header-only libraries for getting data from C++ into awkward arrays. We want to wrap this as a pandas series, so you can have complex data structures in a column of a data frame. More I/O methods. The numerical kernels, we're now released the GIL, so they run faster. And we are having a much-needed overhaul to our documentation. So thank you.
Thank you very much. Next, we have Jared Millman telling us about Spec. And finally, we have Thomas Fan on deck for SciPy Learn.
Hello, everyone. I'm Jared, and sorry about that. But if you maybe saw the online version last year, Stefan van der Walt, my colleagues, talked a lot about, introduced these specs. We're going to be talking a little bit more this year about the Scientific Python project, which the specs are a part of. And as you can see, there's a lot of different opportunities. I'll show this slide in the end, but I just wanted to let you know that I'm kind of announcing things, not really explaining. So the Scientific Python project really is an attempt to unify and bring together the community, lightweight coordination mechanism, because right now, all the projects are separately organized and maintained. So there's a website, scientific-python.org, where you can find some links. At the bottom, you'll see a bunch of social media links, which is more of our community outreach aspect. And you also see a link to these specs over here. So the specs are a little bit like PEPs or NEPs or any of the other enhancement proposals individual projects have. They're different in the sense that there is no enforcement mechanism. We're not the developers of all these projects, so this is an opt-in recommendation system. You can read a lot more about these specs or on the website. You can see the link there. We also have a discussion forum and a couple other different mechanisms for communication, but the discussion forum, I invite you guys just as users to come, but more importantly, we're hoping to get different projects to move their mailing lists over here. And the idea being that if you can tag things, it'd be nice. Well, yeah. And there's BOFs and talks, so you can come and hear more. You can also see there's going to be some T-shirts, so look for people with T-shirts.
Thank you. And last but certainly not least of the track, we have Thomas Fan with SciPy Learn.
All right, you have 3 minutes. All right, so hi, I'm a maintainer for SciPy Learn. I'm going to give an update on SciPy Learn. So our community updates. We have office hours bi-weekly on Discord for contributors to work with maintainers on the pull requests. We also have a communication team, which helps manage our social media accounts like Twitter and Facebook, and also our blog, which has news and updates on the SciPy Learn community. So now, feature highlights from 1.0 and 1.1, which were released from last SciPy. We have spline transformers, which adds nonlinear terms using splines as basis functions. We also have quantile regression, which predicts the key of quantile, this is a linear model. We have a more flexible plotting API with from estimate and from predictions. Then we also have a online one-class SVM, which is the classic gradient descent to solve the one-class SVM problem. There's a lot more features, but those are the highlights for 1.0. 1.1 highlights. We have quantile loss in the His gradient boosting regressor now, so it does quantile predictions, but with His gradient boosting, which is scikit-learn's light GPM implementation. We also have mini-batch NMF, which is an online version of non-negative matrix factorization. We have bisecting k-means, which uses hierarchical clustering for the k-means problem. We have grouping in frequent categories in one-hot encoder, which groups in frequent categories with the one-hot encoder. That's what it says. We have many performance improvements throughout the library, just taking advantage of Cython and OpenMP and better data structures when doing pairwise aggregation. And yeah, lots of performance improvements. It just runs faster. Upgrade runs faster. There's get feature names out in our transformers. So this makes it, and by extension, the pipelines, this makes it easier to get the feature names out of any transformer, and it makes it easier to connect the features inputted to your algorithm to the final step of the pipeline. Ongoing developments. SLEP 6, it's metadata routing. This is a very big topic, and it enables many different workflows that is not possible currently with scikit-learn, such as nested group cross-validation, and so many more. This is something I'm involved in. SLEP 18, which is Panda's output, which is outputting Panda's data frames in scikit-learn transformers, and I'm hoping this will be a thing in the next release. So that's fun. And I'd like to thank everyone, all our contributors, that help make 1.0 and 1.1 possible. Thank you.
Thank you. I'm impressed. All right, they're back. So that's the end of the SciPy tools track for today. We'll be back tomorrow the same time after the plenary. And now I think we're off into a break. So thank you, everyone, and talk to you tomorrow.